Okay, good morning, everyone. Today, we're going to continue the discussion on latent space analysis. We will do a quick review of PCA and the SVD we covered last time. And then we're going to talk about two new techniques known as factor analysis and ICA, independent component analysis. Okay, so let's cover a quick recap of PCA. Right, PCA basically is a technique that finds principal components of a given data set, and then using these principal components to define a new space where the data points can be projected into. Right, and we also know that the property of these principal components in the setting of PCA is such that they basically are capturing the maximum direction of variance, the second maximum direction of variance, and so forth. So that creates some kind of semantic and geometric meaning, of those directions. And then you can basically compute a projection of the data points to this new space using this operation. And then basically you get a new type of representation of the data X, which now has a nice property. They are uncorrelated on their different dimensions in this new representation. Okay, and also you can choose the number of principal components. Use the value of the eigenvalues, and that eigenvalue can correspond to a truncation error as defined in here. Okay, so that's just a very quick recap of the key concepts in PCA. Now, and this is a typical usage of the PCA given a very high dimensional data, say a data cloud of Word documents or images, which are very high dimensional and very hard for you to directly visualize the data points. You can use, say, in this case, 3 principal components to make a projection. And if you are lucky enough, then after the projection, you can see a natural kind of a clustering or aggregation of the data points. So this is a projection of the so-called iris data set. It's a very, very well-known data set for benchmarking some machine learning algorithms. You can see there are 3 clusters, and in this case, the 3 colors gets nicely separated. In fact, if I show this is a PPT, this is a PDF file. In the PPT file, in the PowerPoint file, actually, I have this whole thing even rotating. You can see from different angles. They are really providing a nice separation. There are some, small kind of mathematical treatment of the data for you to do PCA, right? For example, you need to do centering, right? And you need to, centering is the major thing. And then you of course need to compute the covariance matrix of the data to start a PCA. Now, after I move on to the new problem, I also want to maybe do a recap of a few other related concepts which may cause confusion, right? So far, I think in last class, people already asked this question, and I don't think I explained as good as I wished, so I'm going to explain that again. There is a technique known as PCA, and we also talked about singular value decomposition, right? And of course, there is a very generic matrix linear algebraic technique known as the eigenvalue decomposition. So what's the relationship between all these? I bet this is a question that is interesting to get down to the bottom and get it very clear. Right? So this part, again, describe what is PCA, as I just mentioned before. Inside PCA, there are 2 key ideas. One is that, first of all, it is a eigenvalue decomposition technique that you are going to decompose a square matrix into, the product of three matrices. These two matrices, U and UT, are transpose of each other. And then in the middle, there is a lambda matrix as the eigenvector. Right? This is a very typical, eigenvalue decomposition problem. But why it is known as PCA is because this matrix, okay, is the covariance matrix of the data. And by replacing or by defining this matrix to be the covariance matrix of the data, you actually are doing PCA. What you get is the principal components of the data. So that's actually the relationship between PCA and the eigenvalue decomposition. The SVD is also a matrix decomposition, but it is not eigenvalue decomposition, right? It is matrix decomposition called a singular value decomposition, which result in these three matrices. Right, there is a left eigenvalue matrix, eigenmatrix. There is a right eigenmatrix, and then there is a middle singular value matrix called that is diagonal. And the difference between SVD and the PCA is that in SVD you get two eigenmatrix or eigenvector matrix. The left one, this one, turns out to be the same as the eigenvector matrix in PCA if your input matrix here, X, is the data used in PCA, but it is not the covariance matrix. It is the original data, X, the term by document matrix in here. Okay, and then the right, eigenvector matrix is actually the projection of the original data in here into that space defined in here, defined by the left eigenvector matrix. So in SVD, you basically are achieving a very nice effect where you simultaneously get the eigenvector matrix and also the new representation of the original data in such a space, and also the weights, which is the singular value. And then the singular value is actually the square root of eigenvalues. Okay, so I hope I clarified the relationship between these three concepts: SVD, PCA, and the eigendecomposition. Eigendecomposition is a generic linear algebraic technique to decompose any matrix, any square matrix. Okay, and then PCA is when that square matrix is the covariance matrix of the data, and the SVD is basically the direct decomposition of that data matrix, and they related to the PCA if the PCA and SVD are really focusing on the same data set, and then the eigenvectors in PCA and the eigenvectors in SVD has this correspondence, and also the projection in SVD is also basically what's you'll see in the previous operation in here. Sorry. This part. Okay, am I clear in making this clarification? Is that helpful? Any questions at this point? Good, no question. Then let's move on and see some extensions of the PCA technique. Basically, the extensions are just more different ways of computing the projection matrix, and also different statistical interpretations of this operation. Remember last time toward the end of the lecture, I already showed some additional technique, which is replacing the covariance matrix in the PCA with some other matrix, such as the geodistance matrix and so forth, which results in the discovery of some lower dimensional representations, for the manifold to be preserved. Okay, and today I'm going to talk about a few alternative approach which defines newer relationship between the embedding and also the original data. For example, this particular method known as the probabilistic PCA. It is very similar to the results people get in PCA. Okay. I'm trying to see whether I can move the cursor. No, I cannot, but you can see this already. All right, so here we start by assuming a linear dependencies between the projection and the original data. Okay, so here we are taking more of a probabilistic approach and also a variable dependency approach where y is your data that you observed as the data points as a data vector, and x the projection that we want to compute is a did I get it? No, I think, yeah, I think that's right. X, yeah. Y is the observed data, and X is, in this case, the projection you want to compute, but it is latent, that you don't observe it. Just assume them to be a hidden random variable, just like the cluster label, the cluster assignment that we computed in the k-means algorithm and the EM algorithm. And then we define a explicit linear dependency that y is achieved by doing this linear algebraic operation by matrix multiplication. X gets left multiplied with a transformation matrix. We call them sometimes a loading matrix. So this is a rectangular matrix which could be very thin, okay, and but which could be very tall. So what does that mean? The thin part, the column, is basically correspond to let's say k, which are the dimension of the x, the latent space. In this case, we assume them to be small, and the x, the y is the original space, the data you observe. They are high dimensional in this case. Therefore, you can see that the lower dimensional x gets transformed into a high dimensional y through this matrix multiplication. Let's imagine this is the x matrix and this is the y matrix. Okay. And then I would add some noise. Not add noise. Add a mu, which is a way to move the resultant points into different positions in the Euclidean space without changing their direction. It's just the center of the data, basically. You can basically center the data anywhere now. And then plus also a noise. Okay, the noise could be a Gaussian noise. Okay, and we also assume that this latent dimensional x itself is following some q dimensional Gaussian distribution like this. Okay, so now the resultant data is basically this new data y, which is what you observed. But because of this construction, you can actually do some linear algebra and conclude to yourself that it is also following a Gaussian distribution with mean equal to mu and with covariance matrix equal to lambda times lambda transpose plus this diagonal matrix. Okay, once you have this maximum, have this probabilistic procedure of generating the y from the latent x, you can actually write down the maximum likelihood solution to the PCA. It turns out that the results is pretty similar. I'm not going to derive it. In fact, I have a more elaborated model called the factor analysis down the road, which you can see how to make such derivations. But here I'm going to just show you the answer directly so that you can see the connection to our standard PCA. So in the probabilistic PCA, the mu is just the data center, the data mean. That's very, very trivial. And then this loading matrix, which is often understood to be the equivalence of that eigenvector matrix in the PCA is indeed very, very related to the PCA's eigenvector matrix. It is now basically, you can compute them to be this matrix of the original data. This matrix is the eigenvector matrix of the original data, indeed, the same as in PCA, times the lambda, which is the what is the lambda? Well, the lambda is the eigenvalues of that matrix, and then also minus that noise, from the generation process. So remember, this is a diagonal matrix, and this is a skinny transformation matrix, right? Which is k such eigenvectors. Therefore, this one is also a skinny transformation matrix. So you can see how this operation connects to the mu, which is, remember, in the mu, if you remember the first page of the slides, we have this y equals to u times x. That is how you transform the data, from eigenvector to the real data, right? So here it's the same, except that now the matrix for transformation gets a little bit fancy. So probabilistic PCA is very similar, to PCA in terms of the mathematical format. But on the other hand, using probabilistic model, as you will see later, there are some benefits, in getting more kind of a computational convenience and the efficiency. Remember that in the PCA, we talked about a very serious issue about the cost of a matrix inversion, right? Which requires you to do decomposition inversion of the n by m covariance matrix. If you have a very high dimensional data, that could be very expensive. It turns out that using the probabilistic approach, as you will see very soon, we may be able to bypass this very expensive operation using, in fact, our old friend, the EM algorithm trick. Okay, so now having presented the probabilistic PCA, I'm going to now go to the serious business, which is a more general version known as the factors analysis. Okay, the factor analysis takes an assumption which is a little bit more general than probabilistic PCA. So again, starting from a latent variable x, which is assumed to be lower dimensional. In fact, it doesn't have to be, but for the convenience and the straightforwardness of the argument, I call it lower dimensional. And the y is the observed data that you see, which is higher dimensional. Say y is in the 3-dimensional Euclidean space. Okay, and the x is lying in this 2-dimensional plane, for example. Okay, so here we define what is known as a probability generation process, which can help you to define the marginal and the conditional and the joint of whatever random variables. So in here, P of x is literally a lower dimensional Gaussian distribution with zero mean and the unit covariance. You can imagine that it is literally just something that is living in the data, in this 2-dimensional space. Okay, and then y is a little bit interesting. It is first of all resultant from a linear transformation of the x. Basically, x in the lower dimensional space, for example, a point in here, okay, which is defined by its lower coordinate, 2-dimensional coordinate in the plane, gets now defined as a 3-dimensional point in the 3-dimensional space by left multiplying this loading matrix lambda. The lambda basically are just corresponding to the two kind of vectors, defining the subspace. You can imagine they are the eigenvectors, in the PCA case. And then plus a mu, which is the center of the data in the low dimensional space. Therefore, you can see the data in the higher dimensional space doesn't have to be centered. They can be anywhere, centered around an arbitrary mu of unknown value. And then their covariance is a psi matrix, which defines a little kind of noise distribution in the true space. Okay, so you can imagine this is a little ball of a noise space, that is intersecting with the plane, which is a lower dimensional space. Okay. Question: what is the Q here? Where is the Q? In the previous slides, Q is the dimensionality of the lower dimension of space. For example, Q in here equals to 2. Okay. Yeah, number of principal components, same thing, yes. It says that the top Q covariance, yeah, okay, I think the question is explained. All right, so this is the generative story of factors analysis. And the dependence, the relationship between probability PCA and FA is is very, very close. Remember, in the probability PCA, we assume what is known as the isotropic Gaussian distribution or Gaussian noise. But this one follows a Gaussian noise of zero mean and some diagonal covariance matrix. Right, but in the factors analysis, this psi matrix is not necessarily diagonal. Okay, but it can be diagonal if it's easier. Okay, but even if it's diagonal, it doesn't have to be the same in all dimensions. So it's not isotropic. Okay. All right. So what's the learning problem now here? In solving the FA problem. Someone want to
define the problem? I think there's a question in chat. Someone says, you said the loading matrix represents 2 vectors?
Yes. The loading matrix, this one, the lambda, actually are 2 columns, right? And they basically could be understood as the 2 eigenvectors in the PCA case. They're literally just 2 vectors, lambda and this one, in the original space. Okay, now that's a geometric way of understanding that. Otherwise, you could just imagine them to be a matrix of left multiplication. I'm trying to establish the geometric connection between factor analysis and PCA. So there are some kind of analogy of what you see in FA and of what you see in PCA. Actually, going back to the question of lambda, do we know it? This lambda matrix? We don't, right? In fact, the FA defines a problem that is very similar to PCA. In PCA, we are given the raw data, but sorry, I'm going to change in notation. Here, I use the Y rather than X to describe the observed data. Okay, the X are something that we don't know yet. So this Y is the only given data points. It's a point cloud that we have. And in PCA, we need to figure out, in PCA, we need to figure out what is the U matrix, the eigenvector matrix, and the sigma, the eigenvalue matrix. So in here, in FA, we also have Y. What need to be figured out so that you can get the X? Because both PCA and FA, the goal is to be able to obtain the X from Y, right? So in here, what to be figured out?
I do have another question. Someone is asking, what is phi the covariance of?
What is what?
What is phi is the covariance of what?
Of the noise. Phi. You can see here I'm defining, a conditional distribution, right? You can basically say invalidated in the previous slides. no, it is not. Let me write it again. So you can imagine that y equals to mu plus lambda times x plus a noise. And this epsilon noise follows a Gaussian distribution of 0 and phi. That's basically phi. Clear? Yeah, someone answered already. I need to compute mu. I need to compute lambda. Yes, maybe I also need to figure out the psi, right? Yeah, that's the learning problem. So how do we do that? It's a little bit more cumbersome now than the PCA, but you kind of already see some fundamental differences. In PCA, when you want to get mu and the sigma, you typically do an entire eigenvalue decomposition of the original m by m matrix, right? In here, you are going to directly learn the lambda. You already predetermined that you want the lower dimensional to be q, with the original dimension is m, and therefore you only need to figure out this m by q matrix. And this can be way smaller than the m by m matrix. And then you chop off the tail eigenvectors. Right? So that actually could be a place to save computing. And also here, of course, you need to figure out the phi, which gives the noise. Okay, let's see how to do that. Remember, this is now a probabilistic model. We have hidden variables and we have observed variables. Okay, and when we have a probabilistic modeling problem with a hidden variable and observed variable, what are the algorithms that can jump into your minds? EM, great. Yeah, remember that there are 3 layers of. I saw an article. Someone wrote that there are 10 different tiers of understanding for EM. But in here, I think we can understand 3 tiers. The first tier being that if you have a latent variable and also observed variable, you use the EM to figure out the latent variable using expectation, and then you become a maximum likelihood estimation. That's actually a great way of understanding that. Later on, we of course know that it is about maximizing the complete expectation of the complete likelihood, which actually gives you the mathematical justifications of the algorithm and also derive the updates. So we're going to see how these stories, boils down to solving the FA problem. Okay, so we're going to now try to derive some algorithm which help us to estimate the mu, the lambda, and the phi. Okay, and let's see how to jumpstart the EM algorithm. So obviously, if you want to run an EM algorithm, in this, the goal is to be able to write down the posterior distribution of the hidden random variable given the observed random variable. So in Gaussian case, remember this is a Gaussian and this is a conditional Gaussian. How to write down the posterior, of such a construction? Here I'm going to just speak something that is, very standard, but I'm not going to prove them in detail, so you can remember it just as a kind of a given rule. First of all, when you have a Gaussian distribution, you typically don't need to write down any equation for that because the Gaussian distribution is fully characterized by a mean and a covariance. Right? Once you know 2 of these, you actually you understand the entire distribution already. So in here, let's see, we have the mean of the x already because we say that x follows this distribution, right? But we don't have, the mean and the covariance of the y yet. We only have a conditional of y given x. So here, how can we write down the expectation of the x and the covariance of the y and the covariance of the y? So here is a single trick, right? Y is a transformation coming from here, by the way, sorry, this noise just become a W. It was also called epsilon in the previous presentation, but it's a noise term. And you take expectation of this using the transformation, and you can easily see that the expectation of the Y is also mu. Okay, the same as in here. And then the covariance of the Y can be brute forcefully computed by the definition of the covariance, and then you get this value, which is a outer product of the lambda plus the phi, which is the noise covariance. So that's the standard way of computing a marginal distribution of the Gaussian. So in this case, it is the marginal for Y. Okay, and from here you kind of already see some nice properties of the marginal distribution of the Y. They are defined by a mean that is just a add-on component in the form of a m-dimensional scalar, a vector, and then this covariance is actually not a arbitrary covariance matrix. It is made by an outer product of two scaling matrix and plus a maybe diagonalized noise matrix. So what this tells you, it tells you that this is not actually what we usually understood as a full covariance matrix where all dimensions are correlated in some way. A full matrix, dimensional matrix of m by m means that every dimension in the data has correlations, has non-trivial correlations. Okay, and that's usually mean the data is full rank, and it cannot really get so nicely projected into a lower dimensional space. But if your covariance matrix is like this, which means that it is almost low rank, meaning that only a few dimensions in the data is carrying information and others are not. And those other additional dimensions that carries some information may be coming from the noise. Okay, so that's basically what the factor analysis is trying to reverse engineer. Right? Reverse engineer means that you actually don't have the X yet, you have only the Y, but you believe that the X or the Y has this kind of low rank structure. And then you figure out what is the X and what is the lambda and the phi. Okay. So in the EM problem, before I present the algorithm, I need to bother you with a few mathematical details so that you know what the equation really means. These mathematical details are pretty standard, in matrix manipulation for multivariate Gaussian, but they are a little bit challenging for you to always remember. So you just basically try to appreciate that such thing has been derived already, and you know where to look for. Some people remember it, some people just don't remember this term, but at least you know where they come from. Okay. So starting from X, which is a standard Gaussian in this case, I'm talking about the standard manipulation as a primer to multivariate Gaussian. Then there is a sequence of ways to manipulate a joint Gaussian distribution that contains both X and Y. In this case, I just want to make the notation a little bit more uniform, X1 and X2. Okay, and a joint Gaussian can be defined by a stacking vector of two subvectors X1 and X2, and then in this case, their distribution can be also defined by this term, which contains a stacking or concatenated mean of the two submeans, and also a bigger covariance matrix in which there are self-covariance matrix of X1, self-covariance matrix of X2. Remember, X1, X2 are two vectors, okay, and also cross-covariance matrix between 1 and 2 and 2 and 1. Okay, so this is just the definition of the joint Gaussian distribution. It turns out that there are very nice mechanical way of inferencing on marginal of x1, conditional of x1 given 2, and the marginal or conditional of x2 given x1, and so forth, by using just these blocks of sigma and vectors of the mu. It's just a mechanical manipulation. For example, we can write down the marginal of the x2, which is this subvector, okay? And we saw that already. It's basically directly reading off from, the mu1 and this one, okay? The other more interesting result is actually the conditional of the x1 given x2. This is useful because going back to the factor analysis, that is something we want to estimate. We want to estimate x1 given y in the factor analysis. So in here, the x correspond to x1 and the y correspond to x2. So what is the conditional of that distribution? Well, we knew that under a joint Gaussian distribution, any marginal of a subset of the variable or any conditional of a subset given another subset are all Gaussian distributions. So this is a fact that people proved a long time ago. Therefore, in order to determine what is the conditional of, say, x1 given x2, all you need to know is the mean of that conditional and the covariance of that conditional. Okay. So this actually can be easily achieved by following some very mechanical rules of the submatrix manipulation, which I'm not going to derive. Okay, it's algebraic, a little bit hairy to derive all that, but hopefully you can remember it. So the conditional mean of x1 given x2 is defined by its original mean mu1 plus some shifts. And the shifts is basically defined by the differences of your observed x2, minus the the mean of the x2 and multiplied with a few matrices. Okay, and then the conditional covariance of the x1 given x2 also follows this particular sequence of matrix algebra. Okay, just remember this. The virtue here is that you can basically read off all these submatrix that you need to compute the conditional mean and conditional covariance from the submatrices of this joint distribution. Okay. All right. And there are some other matrix algebraic rules. I want to just put it here in case you are interested. For any matrix, which is a table of numbers, you can define its trace, okay, by basically sum over, all the diagonal elements. Okay, and then there is also a rule called cyclic permutation. The trace of these three matrices, is invariant, under cyclic operations of the three component of the three multiplicand matrix. You can take a derivative of the trace with respect to, some other matrix. In here, let's say the argument is a product of two matrices. And then the derivative of the trace of that with respect to one of the matrices is, just the other matrices transformed. Okay. That's actually quite useful because very often we see this quadratic form, in our, data modeling. The x vector transpose times, a matrix in the middle, which could be the covariance matrix in the Gaussian case, and then multiply by the another kind of instance of the data vector. And using the cyclic permutation, you can now move this x into here, and therefore you have the 2x here and this here. And the x times x transpose, remember, is the outer product of two vectors. They become a matrix, right? And then when you take the derivative of A, you have only this thing left. So it's very neat. And the determinant of the matrix if you take a logarithm of the determinant with respect to the matrix, you get the matrix itself. Okay. All right. So these are just some rules we are going to use in a second to derive our EM algorithm. Now let's see how to solve the EM problem for factor analysis. To repeat, factor analysis start with latent variable x following a lower dimensional Gaussian distribution, and then transformed by a conditional Gaussian distribution, of y given x. And here are the parameters of that transformation. And using these two equations, you can actually compute both, the mean and the covariance of x and y marginally, so that you can fill in this and that, okay, as we did already in the previous slides. But also you can compute the cross covariance matrix between the x and the y just by using their word definition. And you find that the cross covariance matrix, cross covariance is actually equal to the lambda transpose. And the cross covariance of y over x will be the transpose of this. Therefore, you plug in these things. Therefore, writing down the joint distribution of x and y in here is actually quite trivial. You basically just plug in, all these matrix building blocks and also the means, okay? And now you have the joint. Okay, so now you see, I started from x. I use the y and given x from the definition, and now I'm going to write down the x and y as a joint using these mechanical operations. And what's next? Well, the next is to now go further and see whether we can write down the distribution of x given y. Remember, in here, we already figured out the rules of writing down the conditional mean and the conditional covariance. We're going to use this rule. And we also have this matrix in here already computed for this particular problem FA, which is in here already, right? So next, we have sigma 1, 1 equal to this, sigma 1, 2, and 2, 1 equals to this, and sigma 2, 2 equal to this. We are going to plug in these three things into here and into here so that we can compute the conditional mean and the conditional variance of that posterior distribution of the x given y. Okay, so the full mouthful of words, but hopefully you get the point that where I'm driving. So mechanically plug this in, you get these two equations. Okay, these two equations are very important because it really, now solves your posterior inference problem. The conditional mean and the conditional distribution of x given y is basically well defined. So we might be happy to start from here and jump to the EM algorithm because now the E step is solved. The E step about computing, for example, the expectation of x when it is observed can directly use the mean and the variance in here already, right? It turns out that that is not quite nice. Not quite satisfactory, I would say. So here I will ask a very tough question. Can somebody help me to figure out what is the computational complexity, say, of figuring out the conditional covariance matrix of 1 given 2, of x given y, say? How much computation is needed? So this is a very, very challenging question. I want to just give it a try. Anyone can see it. Using this equation, by the way, using this equation. I will give you some hint. Size of pi square. Yes. In fact, yeah, it says the pi. Pi is how big? It's the same dimension of the data, right? It's m dimensional. Yes, I saw it. Yeah, dimension of the observed space to the cube, to the power of 3. Yes, so it is m cube. It's a very expensive operation. If you have a high dimensional data of y, this would be a very expensive operation, as expensive as you do PCA, but not quite, getting all these nicer results of probabilistic inference. But because now we are manipulating the Gaussian and using the structure basically of this self-covariance or this conditional covariance matrix, you know that this m by m matrix in here is not necessarily a very full rank matrix, because here lambda times lambda transpose is a tall skinny matrix times its transpose. And this pi is actually a diagonal matrix. Therefore, this the resultant, the whole thing to be inverted is actually not necessarily a full matrix. Okay. In fact, there is another rule called the matrix inversion lemma, which is a little bit difficult to remember. But once you apply it to these two equations, you get a new expression of the conditional mean and the conditional covariance, which is like this. You are in the conditional covariance, suddenly you have the lambda transpose times inverse of the pi and times lambda, which is now like this. Okay, so this leads to this little matrix, which is Q by Q. Okay, lambda size is also, no, lambda, remember, lambda is my loading matrix, which is size m times q. It is that's why it's called the loading matrix. It is to transform from m dimensional data to the q dimensional data, right? So that's the key trick, right? Suddenly here, your inversion problem becomes a q square problem rather than a m cube problem rather than a q cube problem. Okay. Okay, I don't want to stay here for too long. It's just a mathematical trick to allow a easier estimation of the conditional covariance and a conditional mean. If you're interested in the algebraic magic, you want to go to the office hours. Here, I actually want to go forward and talk more about the algorithm itself. Okay. All right. So now basically we are ready to apply the EM algorithm to estimate the lambda. We only know lambda as a placeholder, but we don't actually know its start value yet, right? It's to be estimated. So in our original problem of data likelihood, we know how to write down the margin of y already, right? And you can actually work out the likelihood function, which looks like this. It's a combination where lambda and phi and gets intertwined in complex way inside the determinant of a log of the determinant, inside a inversion and the trace and so forth. Therefore, they are highly coupled. You don't really have a very good hope to derive a clean expression, of the updates. Just like what we see in the EM algorithm, when you do mixture of Gaussian, everything become intertwined. Now, in the complete likelihood, where both the y and the x are given, you have some nice kind of a separation where things gets better decoupled. For example, in here, in this term, you only see the y. Okay, in here, there is a nice linear kind of a relationship between the s, which contains the lambda, and the phi. There isn't another inversion on top of it. Right? So that actually makes the dependency between the two parameters a little bit easier. But remember, here, this x and these S are actually latent. They are not observed. They are random variables. So in our EM trick, you probably remember, we're going to now replace these random variables with their expectations by putting an angular bracket of that. Therefore, the expected complete likelihood, can be easily computed by replacing this term and this term with their expectation, right? And that's why, our earlier calculation of the conditional mean of x, the m1 x given y, and the v of x given y become very, very useful, because x and y are Gaussian, not random variables. Therefore, you can use the mean and their covariance to express the expectation of their first moment and second moment. Okay. Questions? I think we bounded it by the time to invert it. Yeah, let's discuss.
Someone was asking about the time complexity. Like, how did we count the time complexity? And then someone was responding.
Yeah, let's discuss the time complexity later, because I think I said enough, but maybe some of you didn't catch it. When we have time toward the end of the lecture, we can review that. How about that? Because right now there are some other interesting points I really want to miss. Okay, so once we have now the expectation, thanks to our derivation in here, we can basically plug in this into the E step, so that this expected likelihood, complete likelihood, is no longer a random variable. And then in the E step, we're going to take a derivative of this guy with respect to all the parameters that we want to estimate, including the phi and also the lambda and other things. Again, the algebraic derivation will be hairy, but you can inspect these equations if you are interested. You probably don't need to really compute by yourself, because these algorithms are well implemented, but you now know where they come from. In the factor analysis, you are not doing a PCA, right? You are doing some lower dimensional matrix inversion to start a EM algorithm, which allows you to iteratively estimate the loading matrix and also, the covariance matrix of the noise. Okay. Now let's do a side-by-side comparison, right? So in here, PCA, again, your observed data is embedded into a lower dimensional space, and the relationship between these two is the mu matrix, the U matrix, which is the eigenvector matrix. And we do a truncation of the eigenvector. Therefore, this U matrix could also be lower dimensional, but you need to begin by a full dimensional U matrix to do due to the singular value decomposition, or due to the eigenvalue decomposition. And in here, you have this assumption very similar to what you have in PCA between the latent embedding and the observed data, but they follow a probabilistic transformation, and then you can compute their expectation, okay, using this matrix inversion and matrix conditioning type of rule, which is easier for you to to invert and to compute, arguably. Of course, if our latent factor analysis is trying to blow the data from low dimensional to higher dimensional, then you lose all this advantage. And that's a different issue we are going to face in other problems. Okay. And then there's another important difference in addition to the computing, okay, which is so the computing here, I think, is summarized. Here you have a KK, or maybe I used M in the past. Basically, it's the observed dimension. This QQ is the latent dimension. The other component or issue I want to highlight, which is very important, is the stability or the quality of the algorithm, with respect to a change in the data. In PCA results is a covariant under rotation. If your Y experience a rotation of the data, say you just multiply all the data with a matrix to rotate it, then your PCA result will be changing. Okay, they will basically give you back other principal components. Okay, in FA, there is a covariance. Basically, if your data gets scaled, by something, then your loading matrix will also be changing. But if they rotate only, you may get the same lambda matrix. Okay, and you will see why that's the case in a second. This is good and bad. Sometimes it's good because it's very stable in terms of perturbations in data, but it can be also bad because that means even when data are rotated meaningfully, you cannot detect it in your loading matrix lambda. Okay, and in here, well, there are also techniques to find principal components incrementally one by one, but typically you need to find all of them. And in here, you can just predetermine the number of latent factors you want to find, and here you have to find them all. It's not an incremental algorithm in terms of the principal components, but that full algorithm is only relying on a low matrix inversion, low dimensional matrix inversion. Okay, so here are some examples of what you see, right? You begin with the original data matrix, the term document matrix. And in the PCA, you have this correlation matrix, which is a square matrix. But in the factor analysis, what you get is the lambda matrix. And after the loading, you actually will be able to see that your data may actually load themselves to very different factors. Okay, maybe the first few points are highly concentrated on the first dimension and second and so forth. Okay, so this is a nice kind of visualization of the factor loading matrix. Okay, and then go back to the model invariance and identifiability issue. Remember that in our equation for estimating the loading matrix lambda, if you go back to the equation, you will always find that the lambda matrix never appeared by itself, in the likelihood function or in the optimization problem that we need to solve. It only appears by itself when you already infer it and you want to achieve, a transformation like this. But when you do the likelihood, because it is a Gaussian distribution, you need to multiply, the data vector, by its transpose. Therefore, what you see is basically always a outer product, of the lambda matrix. And this actually creates a problem known as rotational invariance, because if now you replace the lambda with a lambda multiplied by Q, where Q is what we know as the orthonormal matrix, meaning that Q times Q transpose gives you an identity. Then whatever Q that you plug in will leads you to the same, outer product of lambda and lambda transpose. That means when you just, rotate this lambda matrix with Q, you are not going to change the likelihood of the data under our factor analysis model. So that actually creates a problem, because you can imagine that two different estimations of the lambda will give you the same likelihood. Therefore, you cannot tell apart which one is which. Okay, so this is a problem known as the identifiability. Therefore, when talking about this loading matrix, and when I mentioned they are two vectors, it's actually advisable not to say too much about the physical meaning of these two vectors. Okay, it's just a loading kind of a mechanism for you to transform the data into somewhere. But this vector itself, are they corresponding to a particular semantic meaning or not? Not necessarily. Yeah, that's actually a reality many people had a hard time to admit, because many people like FA for many reasons, and give you neat results like this one. You seems to be seeing a nice kind of a division of the feature loading. But in reality, if you rotate this matrix by some angle where all these numbers get screwed up, you can still get the same results in terms of the likelihood of the projection. So so this is a controversial issue for FA. But again, the FA algorithms are still widely used because they give you a lot of nice practical value in terms of transforming data into low dimension, and also lower cost in computing the estimations. Okay, I have another 20 minutes. Maybe I should pause here to take some additional questions before I cover briefly another more advanced technique known as the independent component analysis. But let me stop here for a minute and take some additional questions. So just now, quite a few people still were asking the computational issue. Are we all okay now? Sure. Is the number of parameters identified arbitrarily? Number of parameters, you mean the number of, say, dimensions? Or, yeah, okay, yeah. It is like the EM algorithm or k-means. You need to predefine. It's like, I want to project into a three-dimensional space or something. Yeah, this is a choice. Other questions? There is one about that. Okay. What does it mean by lambda only appeared as a lambda? Okay. Let me switch back a few slides. Maybe in here. Yeah. Let's look at the complete likelihood function. Okay, or maybe this likelihood function here, right? If you look at where you see, occurrence of lambda, isn't that they always look like this? That's what I mean. Basically, the way lambda, influence the ultimate likelihood is through a outer product. Okay, any other questions? Cool. All right. I do want to say a few words about the ICA, even though I'm not going to dive in too deeply. But here, let's be a little bit hand-wavy on some of the mathematical details, but hopefully you get the mathematical concept and the design concept right. That's good enough, because the ICA algorithm itself is arguably quite complicated, and no one ever want to implement it. You just download the code if you want to use it. All right, so ICA. By definition, it is looking for components that are independent, right? So in here, we get a lambda, which, gives you a few vectors. And also in the PCA, we get a U matrix, which also give you principal components. But these components are not necessarily showing strong statistical property in terms of, say, independence. Okay, I will show you in a minute what do I mean by independence. Maybe take an example. Suppose that you want to solve this very, very famous problem known as the cocktail party. Let's say, in fact, right now we are on cocktail party. We are talking to each other through a Zoom, right? And imagine that I have 10 people here, okay, talking. and we close the video, and you have 100 people out there listening. Okay, so how can you actually have a concise algorithm distinguishing from what you hear, who is speaking what, right? So that's basically the cocktail party problem. Especially when the voice kind of transmission and the encoding is not of high quality. Maybe our very kind of personal characteristic is lost, or especially when we all speak together, at the same time, 10 people, it will be particularly hard for you to deconvolve them, right? I guess that's just intuitive. So that's the problem. Okay, n source and m equals to n or m greater or smaller than n observations, and how to resolve them. So here, we can see, a real world example. Suppose that you have these two independent sources. One is a sinusoidal kind of wave form, and the other is just a square wave. And what you observe, on the two receiver end could be look like this. Okay, and they are basically resultant from, this kind of linear or nonlinear transformations that one kind of receiver gets, of course, picking up two signals with different weighted combinations. Right? And our motivation is that given this, you want to recover that. Okay, so that's a quite practical problem known as the blind source separation. Okay, and it's more than just reverse engineering this HA matrix. Okay, this is the matrix where you basically received your signal from the source. But your goal is to uncover a form of the source, which could be achieved by reverse engineering the A, but also it could be using some independent approach, other approach, as long as you get the S right. So I'm going to show you what that means. Okay. So here is a sketch diagram of the blind source separation problem, so that we can make now mathematically clear about what our goal is. Signal S transformed by A into observation X, and we want to find a W matrix, which may be the same as the inverse of A, or maybe different, but it's a matrix. We want to demix the signal and get a bunch of U. Okay, and how can we know the U's are nicely demixed? Well, that comes to the notion of independent analysis, component analysis. We call the mu's to be good if they are maximally independent of each other. That's basically the goal we want to achieve. So what does dependent mean? Well, independence usually means that if you have a joint of, say, mu1 and mu2, they can be factored into two margin distribution like this, which is a pretty difficult condition to test. Okay. And how to even enforce this constraint, to a transformation model solution is even harder. All right, so now let's again try to see whether maybe you say, isn't that the PCA is achieving something like that? Isn't that PCA is trying to find a noise on one direction and another noise in the orthogonal direction? And does it mean I'm already achieving separation, independent separations? You may ask that already, right? In fact, in this graph, I have maybe this result to be PCA, and these two sources are orthogonal to each other, right? But what I actually wanted is not necessarily orthogonality, right? I want independence better aligned with original sources, and this independence is, may be, hard to capture basically in a PCA kind of algorithm, which strongly assume linear transformation of the data, say from the X to Y, and also Gaussian noise if you use properties PCA. It is a little bit harder to dive into too deep into that, but here I want to just give you a high-level notion about why covariance or uncorrelation and independence are not necessarily the same thing. Okay, so for example, we know that PCA make heavy use of computing a covariance matrix, right, to compute the principal component, and this is the kind of a covariance of say let's forget about X and Y. Maybe I use X1 and X2, for example. But the goal is that even though your data may have a full covariance to begin the PCA, this is Y, but after, let's say, mu, and after the transformation, you get a V where the covariance of the vectors, the V vectors in the new space is actually becoming decorrelated. So that's actually what PCA is achieving. It's quite nice that the new transform vectors are decorrelated. But decorrelation really isn't still mean independence. So as I said, this is an important property that when Pearson correlation rho equals to 0, it does not mean that these two elements are independent of each other. Okay. Do you want to see an example? Do you have a trying to see? Did you get this statement? Why this is the case? Yeah, okay, a bit tricky. Let me try to give you an example. I'm not going to dive too deep, but let's imagine I have two variables, X and Y, okay? And I want to determine whether X and Y are dependent, and also whether they are correlated or not. Okay, maybe I should say get the following. Suppose that X is in the space of -1 and +1. It's basically two discrete random variables. Okay, and also suppose that Y equals to X squared, for example. These are two random variables. I encourage you to compute the Pearson correlation of X and Y of these two random variables. And you will actually conclude that the Pearson correlation of these two random variables actually equals to 0. They are not correlated. But just by design, you can see that the fact that Y equals to X squared suggests that they are highly dependent of each other. Right. So sometimes when two things, for example, my two signals, mu and mu2, remember these two speakers, if they are, not linearly related, they have a nonlinear relationship like these two. Then, even though when you compute them to have a 0 correlation, they still can be very dependent of each other. So our goal is to find a source or a separation that these two signals still can be discovered because they are independent. Okay, so I'm not going to go in too far, but at least I established here that independence and uncorrelation are not the same thing. So we're at least, we're solving a different problem than PCA. Okay, it's not the same problem. Okay, so let's imagine the problem formulation here. From this graph, our goal is to recover this, right? And it's basically, related to the observation and the source through a few linear transformation steps. So in a sense, what we are trying to find is, this particular kind of equation or, entity that relates the true kind of source from the discovered source. They don't have to be the same, but this guy has to preserve independencies. Therefore, they should have the following kind of a matrix structure, where C should be a diagonal, which really does not have any correlation, and P is literally a permutation matrix whose only effect is to permute, different the ordering of the sources. If my V matrix, as a result of discovering the W and A, is of this property, then I claim that I successfully recovered all the sources up to a permutation, maybe up to some kind of a scaling, differences. Right. So this condition could be used as a constraint, in our qualifiers of the solution to W. And then how to enforce, independence. As I said, testing independence is very, very difficult and hard to enforce. So people come up with a term called non-Gaussian entity. It is recognized that if you recover the mu such that they are as non-Gaussian as possible. Well, how do we mean by non-Gaussian? Well, we're going to introduce a few kind of measurement in a second. Then, everything else be the same in terms of construction error and, and matrix decomposition. Then you are likely to have, the sources to be independent. This is originally a guess, but later on people proved it. Well, the intuition is that by staying Gaussian is invariant under orthogonal transformation. As I just mentioned, in the case of factor analysis, you can see that this kind of rotational orthogonal transformation, is not affecting the estimation of the lambda. And as you can imagine, if such lambda are to be recovered, and when you get the x to be transformed in that way, there are high chances that when you rotate them without causing any harm, you are not going to, this cannot be a nice kind of highly independent, sources that you can identify. Because if they are the true sources, they are not they shouldn't be, a covariant, of such rotational effects, right? Okay, so now the I transforms to non-Gaussian entity. And non-Gaussian entity is actually easier to enforce because they can be measured. For example, people can use a term called kurtosis to measure whether a variable is Gaussian or not. You can use mutual information, negative entropy, and a few other things to really quantify the magnitude of a non-Gaussian entity. So that becomes now the loss function, over the solution of the matrix estimation problem. Remember, in the FA, our loss function is a likelihood function, under a Gaussian distribution, and that's actually where the Gaussian entity is strongly reliant on. In here, we are defining new loss functions, which has nothing to do with Gaussian. Okay. So that's basically the spirit behind what is known as the fast PCA algorithm. The algorithm started with some pre-processing of the data, which includes centering and whitening. And these are the equations being used, which essentially transform to, recognizing, a particular way of transforming, the observed data into some other more nicely behaving data, which are centered and whitened. Okay, so this is a linear transformation. That's very easy. People can do it without too much hassle. Then with the transformed data, with the whitened data, you are going to run what is known as the fast PCA algorithm, which now I don't want to explain. We don't have time to explain this in detail. And it is a bit complicated to understand the tricks behind it. But at a high level, it is a fixed point iteration, which actually maximize the measure of non-Gaussianity. Okay, so that's the most important thing. You can imagine that you can have a Newton's algorithm or a stochastic gradient algorithm to do the same. Yeah, indeed, there are other versions, but the fast PCA use a more sophisticated version, which involves first order derivative, second order derivative of the non-Gaussian loss function to make the algorithm converging very fast. Okay, and here are the example non-Gaussian additive measurement functions. This particular algorithm used, but people can plug in other things. So just to sum up, the ICA algorithm basically is trying to solve the signal separation problem and demixing problem. And the basic idea is to really reconstruct from the observation data those independent sources by maximizing non-Gaussianity and and still using a linear transformation between the observed signal and the transformed signal. So you can see ICA, FA, PCA all have some similarity, which is about a transformation of the observation through a matrix multiplication so that they go to a new space, either of low dimensionality or of principal components or factors. And in this case, it is a new dimension, a new space defined by independent source factors. And here the loss function is not a likelihood loss, not a maximum covariance loss. It is a maximum non-Gaussianity loss that leads to the estimation of the W. Okay, hopefully, I'm giving a story that ties together all these different techniques, but still show you the differences of their utility and also their operation. That's the end of today's lecture. Any additional questions before we close?
Can I ask a follow-up on the rotation invariance stuff?
Sure, please.
So like my understanding is that since we're using expectation maximization for factor analysis, like we end up with rotation invariance, like because that's like we saw that like the lambda t term in the likelihood expression.
Mm-hmm.
So like if we were to use like expectation maximization for like for a PCA as well, would that also be like rotation invariant?
Let's see. That's a good question. It's not because of the expectation maximization. Okay, it is really because of the loss function. Remember that the loss function. Remember, EM algorithm is a gradient algorithm, right? It's a coordinate gradient descent algorithm, so it's an algorithm. It actually doesn't change any results if your loss function is designed in a certain way. In here, our objective function or the loss function in FA is the Gaussian likelihood of the data. And that's where you see the lambda times lambda transpose, right? So in the PCA, it's a different loss function, right? It is the loss of defined by the variance of the data. So you need to go back and examine that particular form and see whether there is an opportunity for you to left and right multiply some orthonormal matrix in the eigenvalue, the eigenvector matrix, and see if that changed the loss or not. You can actually check by yourself. If that does change, that means it is sensitive to rotation. If it does not change, then it's not sensitive.
Okay.
Yeah, so I'm giving you not a clear answer, but I give you a method of testing your answer. Any other questions? This is a great one, by the way. I think it's better to give the validation of the answer rather than straightforwardly the answer itself.
Yeah, I just forgot that we're like using a different loss for PCA.
Yeah. Yeah. Cool. Great. Okay, I will see you next week. Okay, Ziv is going to take over for the next couple of lectures, but I will see you soon, in later part of the semester. Thank you. Bye.